Hi, welcome to the bootcamp. So today in this topic, we will be talking about like EKF and AEKF based SOC estimation. So before that, I'll just give my introduction. So myself Krishna, and I'm working as an application engineer at Decibels Lab Private Limited. So I will be taking care of most on like algorithm development and implementation on the hardware side. Yes. So yeah. So with this topic, we'll go to the like not to waste the time. Like we'll directly jump into the like agenda. Okay. So as we showcase, if you see over here, we'll start with understanding the overview of the Kalman filter, and next to the introduction to the adaptive extended Kalman filter. So some classification like I have given as heading like what could be the classification of AEKF. AEKF is nothing but your adaptive extended Kalman filter. Okay. Yeah. And then we'll try to do some comparison matrix with respect to the EKF and AEKF. So comparison matrix means we'll just try to differ like what could be the like pros and cons with respect to each. Okay, if you try to compare to each other, like what could be the pros and cons. Yeah. And then like we will discuss about results, discussion points on EKF and AEKF based SOC estimation. So in my case, I have a like Kalman filter based SOC estimation, that is one with respect to the EKF and AEKF. Okay. So it is like with that we estimate the SOC of the cell or like the battery pack, and I have results of both like the SOC estimation based on extended Kalman filter and SOC estimation based on adaptive extended Kalman filter. So we'll just try to do the comparison. So like how they are going to be differ on it, and then we'll talk about like validation points. Okay. So it means uh, when you take up any like a design point of view or some algorithm development or some any calculation, like if you do some algorithm and you are getting some results, so the one thing we need to say that is it correct, right? Is it a validated result? Okay. So how can we validate? Like when you talk about like SOC, there are other parameters such as like SOH, SOE. Okay. So how can you say these are like correct, right? So on what basis we can say these are correct? Because when you talk about these SOC like SOH or any other cell parameters, they are not direct measurement. Like they are indirect measurement, not measurement. We call it as like estimations, right? So knowing the capacity of the cell, we come up with SOC like by getting to know the instantaneous capacity, and knowing the overall capacity over the period of the cycle, we can come up with SOH, and even based on the cell resistance, we come up with like SOH estimation. So we identify some other parameter of the cell. With these parameter, we try to correlate and bring SOC, SOH kind of. Okay. So with this, we can say that they are not like a direct measurement, they are indirect. So how these can be validated? So on what basis we can validate? So that we'll discuss in brief. Okay. Yeah. So I hope I made some clear understanding on the agenda. So yeah, with this I will move ahead. So let me know like if any like doubts, if you find in between, you can just put in the chat box. We will like we'll try to like see the doubt clarification at the end of the session. So the Kalman filter steps. So first we'll try to discuss about like steps. Like one step will be of like not to worry about the step number right now here. Okay. So just like consider one step is predict. Second is like you can say it as Kalman gain estimation. Third one you can say is update. Okay. So not to worry about these like patterns. Okay, I'll just go to the next slide, not to make you confused. Yeah. So the first step is predict and Kalman gain and update. So we'll try to see like what exactly these are and how the general Kalman filter we represent. Okay. Yeah. So it is a bit of advanced topic. Okay. Yeah. So here you can see on the flow diagram or something like a block diagram, you can see there is some initial state, previous state, and like the new state, or you can say it as a predict step. Okay. And then Kalman gain and measurement from the sensor and the update step. Okay. Yeah. So we'll try to understand like what they are. When like we'll start with these predict step itself as a initial step for now. Okay. So in this predict step, like you are going to like predict the state. Okay. So now you can like ask the question that like what could be the state, right? In like just going in like into the Kalman filter, we'll just try to see. We represent a system. Okay, we can represent a system in a mathematical form. So you can take a cell, you can take a like motor. Okay. So you can take a car, right? So for a cell, we know if we apply the load means like where you can connect and you can draw the current. Okay, in simple, or you can do the charging to the cell. So if I apply the load or if I start charging, we know how it behaves, the cell, in the real time, right? In the same way, if I apply the current or something to the motor, if I give the power to the motor, so it will start rotating, right? So we know like how it gives the response. And for the same way, car, if I start like applying the acceleration pedal, like like how it is going to give the response. That is, it will produce the acceleration, later velocity, and you can see observe the change in the vehicle displacement or the position, you can say, right? So all these behavior, we say it as a behavior. Okay, so the response of your system, we call it as a behavior, and that behavior can be represented and controlled through a mathematical equations. Okay, so later these mathematical equations can be written in the form of transfer functions or into the state space equations. Okay, so right now what you're seeing here, like we represent the system here, it's mathematical, what you call the equations in a state based manner. Okay, so we represent uh, whatever we estimate or whatever the behavior we want to see, those we represent in a states, and we call it as a states. Okay, so yeah, so right now you just see only this equation, which is marked under the red line. So this is a updated, we can call it as like predicted state. Okay, and this is a state, so you can say like what exactly this contains, right? So if my system is cell and I want to estimate the SOC, and I will get to know the terminal voltage of the cell after applying the load. So I'll just type terminal voltage. So these can be my states. Okay, yeah. So right now, like SOC and terminal voltage are like states. How these are further affected, right? So which parameter is affecting the SOC, which parameter is affecting the terminal voltage? So it is the current, right? If you apply the current, if you discharge the current, these values are going to change, right? So where you are going to insert this current value is inserted at this matrix, that is U. So we call it as input matrix. Okay, yeah. The last one is noise. Right now we won't focus on this part. Let's forget this part. Okay, so this is the state where we are going to represent the like parameter which we want to estimate, and these states are influenced by some other parameters. So we represent that in a UK matrix. So we call it as an input matrix. Okay, yeah. So let me clear. So we got to know what is X and U. So in the similar way, A. So like I can call it as A matrix is a matrix where with this matrix, if you multiply with the state matrix, you can convert that like matrix into the present time. Okay, for example, like if this state, right? So this is of x of k minus 1. So if x of k minus 1 is represents the previous state, where you can see over here. So this is a previous time step, right? In order to update to the present time step, like we multiply like A matrix. Okay, yeah. And the same with respect to the B. And once you like add both of them, you will get the predicted step of present time step. Okay, yeah. So this is with respect to the like state, like predict step, predicted state. Okay. And then there is one more step, one more like equation we do in the predicted state, that we call it as process uh, covariance, noise covariance. Okay, like covariance matrix you can say. So in simple, what I can say that this P of K, some dash is there, right? It is nothing but a error in estimate. So if this is your like estimate, and obviously there is going to be some error, right? So that error in estimate, uh, it is represented by this equation. Okay, so you can see like A matrix is nothing but the A which is we used for the state update. Okay, sorry, for the state predict, and we here we have taken of A's transpose, and then P of K minus 1. So this is of previous state. Okay, we will explain this part, like how this previous state has to be considered, all the stuff. Yeah. So in general, like as a totally, we got to know that in the predict step, one we get that is state predict, and the like that is estimate, and the error in estimate. This is error in estimate, and this is estimate. You can call it as estimate, and this is error in estimate, uh, which is a part of the predicted step. Okay, and then you can go to the next step, that is Kalman gain estimation. So what are the inputs for the Kalman gain estimation? One is error in estimate, here also error in estimate, and there is R. So this R, we call it as like sensor noise. When you take up uh, the measurement, or like for example, the current you are going to like sense it from the sensor, the voltage of the cell you are going to sense it from the sensor, right? So based on the accuracy of your sensor, this sensor noise is represented. So you are going to consider the sensor. It means you can say it as error in measurement. Means on the measurement, you will be estimating the cell parameter, that is like voltage of the cell, right? So whatever you measure from the cell voltage with the like the sensing circuit, so that is not 100% correct. So it also has some error. So that error is represented by R. Okay. Yeah. So you may confuse with this one. Like what could be this like process like noise or something. So this like error in estimate, process covariance, uh, that represent that, saying that there will be some error in your theoretical model. Okay, so we call it as like theoretical model. You can say is a digital twin of the cell. So initially I was saying that if you represent a cell behavior in a mathematical form, we call it as a cell model. So that cell model is not 100% correct. It also has some error. So that error is represented by covariance matrix. You can say it as like error in estimate. Yeah. So once you have all these inputs, you will get to know the Kalman filter. Okay. Yeah. If you come back over here, and once you know the Kalman gain value, sorry, it's a Kalman gain value, you can go to the state update. So here it is a state update, and this is the equation that this one is coming from here. Okay. So this Kalman gain will be like coming from here. And y of k is coming from here. And x of k is again coming from here. Okay. Yeah. So with this, you will come up with state update. Okay. So this, whatever you get from this particular block, you can take it as a final output, or if you have further estimations, we can make use of them as previous state. Okay. So the present state updated value, that is x of k and p of k, can be acted as previous state for the next predict step calculation or estimation. Okay. Yeah. So yes. So you might be confused, like what could be the previous state and the initial state. So here, like when you are doing it for the first time estimation, you have to initialize the state with some value. Okay. That is x of naught and p of naught. So for the first time, these initialized state will acting as a previous state for the state predict. Okay. Yeah. So once once it is initialized, it won't be used for the next round of cycle. When you go for next round of estimation, so whatever you get here, this can be used as a previous state. Yeah. So this is like a brief overview of the Kalman filter. Obviously, it's it's not that easy like to understand in a first attempt. So we have to like see the different perspective of like the equations or the explanation or anything. So we'll get to know. Yeah. So here, like when we talk about like Kalman filter, okay, there are n number of filters. Okay, again in the Kalman filter, they are divided into like classified into different sections. Like here in the initial section is like linear Kalman filter. Okay. Yeah. So let me show you here. So this you can take it as linear Kalman filter. Extended Kalman filter, unscanted Kalman filter. So like these further extended and unscanted, when the system is non-linear, right? These come into play. When the system is non-linear, when the system is linear, you can use the simple Kalman filter. Okay. Yeah. So my question is that like our like agenda of the boot camp, that what is like EKF, like not EKF, like AEKF. Wait a second. Yeah. AEKF. Right. So where this adaptive extended Kalman filter comes. So as we look through the like classification, that like linear Kalman filter, extended Kalman filter, unscanted Kalman filter. So under the section of extended Kalman filter, some more improvement to the extended Kalman filter, we call it as a like we call it as adaptive extended Kalman filters. So what exactly the term adaptive refers to? Okay. So I'll just try to give some brief points. Yeah. So while I was explaining about the overall about the Kalman filter, I didn't talk about these noises. Okay. Process noise that you can neglect this one. You can take is like Q and R you can take. So this process noise and measurement noise. So we didn't talk much about these things, right? So like in extended Kalman filter, these noise values are like constant. Okay. Over the period, like your predicted or like updated value comes near to your true value. Let's assume that this is a true value, what I am trying to draw here. And this will be my like updated value. Over the period, it will come near to the true value. But again, we see some like gap between them. Like it is because of having the constant noise. Okay, Q and R. Whatever the values we fed in the initial, so that won't be updated. Like it will be like giving or like providing or feeding the constant value here and here for every like cycle of calculations or the estimation, right? So that is one of the like drawback you can say of only extended Kalman filter. So what exactly this adaptive extended Kalman filter that here it updates that Q and R. So this will be in dynamic in nature. Like it will be updated for every cycle of estimation. Okay. So, so let me show you like what could be the difference. So like I'll just try to like show you. So this R, right, and Q. So if you take this, it is the same. Like some like most of the steps are same. So that let me say, yeah, this R measurement covariance and the state covariance update. We introduce like Q. Okay. So we usually used to use this Q to update the covariance matrix. And for the measurement, we used to use this measurement covariance update. Okay, this R value. Yeah, for the Kalman gain, you can see here. So we like consider this measurement noise. So if I want to show you, make it clear. Yeah, in the same here, uh, these two values, this one and this one. Okay, initially they were constant. Now we are making them as a like dynamic where for each cycle of estimation it will be updated, this Q and R, by introducing some steps. So that we'll see. Yeah. By introducing some steps, we call it as like a residual based adaptive estimation and a residual based. Okay, this should be of innovation. A small mistake here. A residual based innovation estimation. Okay, one with residual based adaptive estimation and other with residual based innovation estimation. Okay, or simply you can say it as residual step or innovation step for the updation of R and for the updation of Q. So it should be Q, some typo mistake. Yeah. So yeah, let me. So these two, like the Q and R dynamic comes under a section of covariance matrix, covariance matching approach. So what is this covariance matching approach? Okay. So when you talk about adaptive Kalman filter or adaptive extended Kalman filter, so like it is nothing but updating the noises. Okay. If you just say only extended Kalman filter, there is no update in a Q and R. If you take adaptive extended Kalman filter, there will be update in a Q and R. Okay, with its residual and innovation step. So this can be done with the different approaches. One with the Bayesian approaches, correlation approaches, covariance matching approaches, and maximum likelihood approaches. So in my case, like we have worked on covariance matching approaches. Okay, so this is example of covariance matching approaches, which only deals with the Q and R, updating the Q and R. Okay, yeah. So all these also like talks about Q and R, but yeah. So for our case, we have like considered this covariance matching approach. So we call this as a covariance matching approach. Yeah. So this derivation, like you can find in some papers. Okay, you can just Google it out here. Yeah. So in terms of step, like, so there is a initialization of state, that is X and P. Okay. And then you can go for like X predict and P predict. At the step one over here, state prediction and like P predict, that is coherence, like process coherence matrix. And the next step, that is in the second. So we come up with the innovation step. So what exactly in the innovation step we do, right? So this is, we get it from a measurement value. And this is a predicted step here. So measurement means from the sensor. So let's say like a voltage from the sensor, and this is a predicted voltage. Okay. And you do the calculation with the matrix H, and you will get D of K. This is like innovation step. And next you go for correction step. So this nothing but like update step itself. You can see this is a Kalman gain. This is a predicted step. And this is a state update. And D of K is nothing but a difference of measurement and the predicted state. So that is nothing but this one. Okay. So if you remember the previous here, this one and this one are like both same. Okay. Yeah. So once like you got to know the correction, like you call it as you can call it as like update state, then you can go for the residual estimation. So again here it is required. uh, so with this update state like or the correction state, you can again going to subtract from the measurement. So whatever the output you got it as residual output. So this innovation, that is d of k and residual e of like k. So further you can see they are sent to their respective blocks, that is at state covariance update, where we are going to use d of k over here. This is equation is nothing but here for the q estimation, right? These dk and dk transpose. So these two we got it from the innovation step. K of t and k is they are nothing but the Kalman gain. Okay, this thing, this value, this value. This q is of previous. Okay, and now the left part is alpha. So what is this alpha? Okay, if you see over here, you can also see the alpha over here. So what is this alpha? So this alpha is relates to the forgetting factor. This is again like some advanced topic. So I don't want to go much into it. This alpha is always defined between 0 to 1. Okay. So let's say like 0 0.3, 0 0.4, 0 0.5, 0 0.6, something. So if the value near to the 1, for example, like 0 0.8, 0 0.9, 0.95, okay, it means it depends more on its previous state estimates. So for example, in the like last cycle, like in the previous state, you have got some value like voltage is equal to some like 3.45 or something. So in the next round, like v is equal to v like plus 1. So it is of next calculation. So here like this 0 to 1, like if it is 0.9, 0.95, means it depends more on the previous value. Okay. So if it is like 0.3, 0.2, that dependency on the previous values reduces. So that what exactly the alpha refers to over here. Okay. Yeah. So now like the Q we got to know. And next, like once you calculate the residual step, that you are going to update your measurement covariance. That is measurement covariance update. So this R of K. So what are the inputs? The previous R value, measurement noise, and then E of K, like E of K of transpose, and this is comes from here, and H matrix. So this E of K, uh, that is nothing but this residual step. Okay, so this equation is nothing but over here. Yeah, it is the same. The alpha which is defined over here, it also like defines the same, that it is if it is like more towards the 1, it means you depending like more on the previous steps. Yeah. So once you like put all these equation, this value will be like variable, like it becomes like dynamic. Only initialization you have to do. Later, further updating, it will be taken care by itself. Okay. So you might be like thinking that why it is required, right? Why can't we give it as a constant? Why can't we like give it as like a constant, like this Q and R, right? So at some scenario, the sensor like if you give the sensor, let's say like current sensor, okay. I have seen like many current sensor like profiles, all the stuff. So in that, what I can say that uh, if I am measuring from 0 to 5 amps, the error will be like 1%. Okay, I'm just taking random example. And if I'm measuring from 10 to 15 amps, the error will be like 1.5%. So these errors like is going to be varied. So if I am giving the constant, so it will affect my like final output. Okay, like the final state update, what I can call it, right? So it will be affected. It may not be near to the true value. It may deviates from the true value. So that's why like making this dynamic and asking it to update by itself. So with that, we can say like the model will try to tends more towards the true value. Yeah. Okay. So this is with respect to the like adaptive extended Kalman filter. Like we'll just try to like discuss some comparison matrix. So the steps involved, okay, in extended Kalman filter, like the steps are like one with predict, Kalman gain, state update, and measurement, all the stuff. So in the adaptive Kalman filter, we see some extra that residual and innovation and Q and R update steps. Okay. So with this, what I can say, right? The computational requirements for the controller, it will be higher compared to your normal EKF. Okay. Yeah. So even you can bet on that the result accuracy will be better than EKF. Like unless until it depends on the other factors, but with the comparison you can say. Yeah. And some more like comparison that Q and R values will be constant since the initialization in the extended Kalman filter, but here it is going to update. Or you can say dynamic. Yeah. Okay. Like there might be some more. Like I just put it across like 4 values, like 4 parameters. Yeah. So let me clear. So with this, like I'll just try to like look for some tested data. These test data is of SOC estimation, one with EKF and one with AEKF. Okay. Yeah. So let me go. Yeah. I have like bought two like graphs over here. One defines with a terminal voltage of extended Kalman filter base, and one with the like adaptive extended Kalman filter. So I have like cell model and data, and like I ran with some current profile, and this is what the response I got. Okay. Yeah. So in this case, I kept alpha as 0.1. So what is the alpha? If I just go a little back over here, yeah, this is the alpha, right? So this value is like 0.1, and this is my response of my model. Okay. And on the other hand, you can see from the same model, if I have plotted the SOC of EKF versus SOC of AEKF. So yeah, you can see some like minor like some changes over here at over the period of discharge. Okay, when you see like drop from almost like 70-60%, you can start seeing the deviation. Okay, and let me show you the next one. So this is with respect to the 0.2 as alpha, and you can see the graph. If you compare with the 0.1 and 0.2, you will see some difference. So this is the SOC graph. So I cannot say that like what I'm seeing this value, or like it might be this value, it is 100% correct. Okay, like comparing it to the extended Kalman filter, because it again depends on a lot of factors, like what we considered, that what matters. So yeah, right now like validation has to be like we have to work on it. So right now these are some like uh, graphs. Okay, let me show you for the next, for alpha. If as I consider the alpha like 0.3, okay, and 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. Okay, so as I go on increasing the 0.9, the deviation between, okay, let's forget about this SOC. If you only consider the terminal voltage graph, like you start the deviation between the two graphs is going to increase. Okay, yeah. So many people thinking that how we can select this alpha value, right? So it depends on lot of parameters. Lot of testing has to be carried out. Testing means like not the cell testing or something like that should be the part of it, but on the other part, that how much our sensor accurate they are. Okay, like if I'm getting some data from my sensor, let's say like I'm getting current, let's say like I'm getting temperature of the cell or like voltage of the cell from the measuring circuit, how good the value is. Okay, so how much we can trust on it. So based on that, we come up with some like selection of this alpha. Okay, yeah. So at the end, these sensor measurement data leads to your validation also. Okay, that we will talk in the next part. So these are some results, and yeah. So yeah, now like I will try to discuss on the validation points. Okay, so when I take up like if I say I have estimated SOC through EKF. So Okay, I'm getting some value like this. Okay, so I got some SOC value here. Like, how can I say that whatever the SOC value I got, it is correct? Okay, like, how can I say that it is more near to its the accurate value? It again depends on how much sensor data you are going to believe. For example, if you take up the EKF based SOC estimation, like, you are going to feed the voltage value, current value. Okay, so like, how accurate these are, right? So with that, you can like compare to your uh, results. For example, so assuming that one graph I got it from my Kalman filter model, okay, and the other graph I got it from my cell cycler. Cell cycler means testing machine, cell testing machine. So I discharge it. I kept the cell and start discharging it from some particular C rate. I got the voltage curve, right? So with your Kalman filter model, that is in the EKF based SOC estimation, you also estimate the terminal voltage. So you start like, once you get to know the terminal voltage from your model, you try to like overlap with respect to the machine data. So how much they overlap, how much the deviation shows. With that, you can like start with one step that for the validation. Okay. So yeah, these are some like validation points, like how you can conduct the validations on the EKF. So once you get to know the terminal voltage from your machine data and from your cell model is almost like overlapping on each other. With that, you can go for saying that my SOC estimation is like good. Okay. Yeah. Because we know that SOC is not a direct measurement. It is like correlation with some other parameters. Okay.